Hello and welcome. In previous videos, we've taken a look at the concept of integration for multivariable functions. And we know that we can use a double integral to calculate the volume of some kind of region that's bounded by a function of two variables and some domain of integration. Whether those two variables might be x and y, or potentially r and theta if we want to use polar coordinates. But now, what if we want to maybe sum up some quantity that is defined as a function of three variables within a volume? Maybe that's dependent on x, y, and z. Well, that will give us what we call a triple integral, and that's what we're going to focus on in this video. But let's start off with just how integrals can be extended by one dimension at a time, starting off with single variable calculus. Well, our original definite integral in single variable calculus was nothing more than just the integral of some function f of x over an interval from a to b. Now, we can visualize that here as a single dimension interval from a to b, and we can label that interval I. And geometrically speaking, what this definite integral gets us is it gives us the area of this shaded region bounded by the x-axis and the function y equals f of x. Now, let's go into multivariable calculus and just recap what we learned about the double integral. The most basic example of a double integral is where we're integrating a function f of xy over some rectangular region R. And here I've just given two intervals, an interval for x from a to b and an interval for y from c to d. Well, that would define a rectangular region on the xy plane. That's our domain of integration. I'll shade that in here, and we'll call that region R. Now, geometrically, what we get as a result is a volume bounded by this function f of xy, which defines a surface in R3, and the xy plane over this rectangle. That gives us a solid region. So we can still try to make sense of what we get as a result. You can see that we have area for a single variable integral, and we have volume for a double integral. Now, what does a triple integral look like? Now, for a triple integral, of course, we're going to be starting off with a function of three variables and integrating it over some domain of integration in R3. So let's start off with the most basic shape that we can come up with. We'll just use an interval for x from a to b, an interval for y from c to d, and an interval for z from r to s. Well, that would define a box in R3 then. I've labeled that box B, and we can shade that region in as our domain of integration. But the tricky part about a triple integral is that we know that we cannot sketch a function of three dimensions. F of x, y, z takes every point in R3 and defines a unique numerical value at each of those points. And we have no more dimensions left to be able to visualize that value. So while we can at least visualize the region of integration, it's kind of hard to imagine what this triple integral gives us as a result. But that doesn't stop us from defining it as a Riemann sum and converting that into iterated integral form just like we did with double integrals before. For a triple integral over a box B, let's define B first here. That's the set of points x, y, z, where x, y, and z are all defined to be within these closed intervals. We can also decide to write that in this square bracket notation with Cartesian products. The triple integral, as you can probably imagine, will be defined very similarly to how we defined the double integral as a Riemann sum. To come up with this triple integral definition, we will just simply divide our intervals a to b, c to d, and r to s into subintervals. We can see L subintervals, M subintervals, and N subintervals for x, y, and z correspondingly. We're going to take the limit as L, M, and N all go to infinity, and when we subdivide the box into each of these smaller pieces, we have smaller sub-boxes. And we'll pick a point x ijk star, y ijk star, z ijk star in each of the boxes. That will give us just a sample value of f, and then we'll multiply that by the volume of each smaller sub-box, delta v. Delta v is just simply equal to delta x times delta y times delta z in Cartesian coordinates, where delta x, delta y, and delta z is the width of every little subinterval for the corresponding intervals. Now, let's not focus too heavily on Riemann sums because this is a very terrible way to try to actually evaluate a triple integral in practice. As you can probably imagine, a triple integral can be converted into iterated integrals where we will have three separate boundaries on z, y, and on x. Since this particular region is a box, then we can see that the boundaries on z will be from r to s, the boundary on y will be from c to d, and the boundary on x will be from a to b, and we have our iterated integral form. Now, we can choose various different orders of integration, but because we have three different variables now, we actually have 6 possible orders for integration. We have this classic order dz, dy, dx, but we have 5 other orders to consider. Luckily, when our region of integration is a box like this, it doesn't really matter which order we choose. So let's start off with a fairly straightforward example where we can integrate a function of 3 variables over a box B. Suppose we wish to evaluate the triple integral of 12x squared y cubed z dv over the region B, where B is defined as a box from 2 to 4 for x, 0 to 1 for y, and 0 to 3 for z. Well, right away, it's pretty easy to put this into dz, dy, dx form. Those 3 intervals become the boundaries on each of the integrals. And just like with double integrals, if we can factor this function of x, y, and z into separate functions of x and y and z separately, then we can actually integrate separate integrals and multiply their results. The 12, for instance, can come out front, and then we can integrate x squared from 2 to 4 dx. We can integrate y cubed from 0 to 1, since that is another factor, and we can integrate z from 0 to 3 as the remaining factor. All 4 factors here are now separated out, making the overall process much easier. All we need to do is apply the power rule 3 separate times, 1/3 x cubed, 1/4 y to the 4, 1/2 z squared, and then evaluate each of the definite integrals. At any point in time, if you wish, you can take those fractions right out. 12 times 1/3 times 1/4 times 1/2 is just 1/2. And now we can plug in our endpoints for these definite integrals. That gives us 64 minus 8 times 1 minus 0 times 9 minus 0, all divided by 2, which gives us a value of 252. Now, if you're trying to make sense of what this 252 really means, be careful here because a triple integral is where we're integrating within a volume. This result doesn't give us volume necessarily. We have a function that is dependent on each point in that particular box. A good example of a function of 3 variables is density, where we might have the density at each point in this box be dependent on the position in the box. If we wish to go back to that definition of a Riemann sum, then what we're doing is taking the density of each individual sub-box multiplied by the volume of that sub-box. Density times volume would give us mass, and summing up over each of the little smaller sub-boxes will give us the mass of this solid. So there's a good example. 252 might be something like kilograms for this solid, which we might be measuring as a volume in maybe cubic meters or cubic centimeters. Another example of a function of 3 variables would be something like temperature. We might be wanting to sum up the thermal density of this particular object, and that will give us the total heat energy within the solid. Just a couple examples of what that 252 might mean in a practical scenario. Now, of course, we're not always going to be integrating over a perfect box. Let's take a look at more general regions in R3 now. For general regions in R3, let's just define E to be a closed and bounded set, where closed would mean that it includes all of its boundaries, and bounded meaning that it doesn't extend on infinitely in any one direction. Let's start off with what we would call a Z-simple region. Now, a Z-simple region is where our function is bounded by some bottom surface and some top surface, which will be functions of x and y. So over some region D on the xy plane, we can say that z always varies between u1 of xy as its lower boundary and u2 of xy as its top boundary. These are surfaces, so we actually can view this from the positive z-axis looking down and just see this top surface in blue, u2. And if we were to view this region from the negative z-axis, we should only be seeing this bottom surface in red, u1. That will allow us to at least iterate with respect to z first. Effectively, that's turning our triple integral into a double integral. We're going to turn this triple integral over a region in R3 called E into a double integral over some region in R2 called D. And our first iteration is with respect to z, and z ranges from u1 to u2 as functions of x and y. But that still leaves us with a double integral over the region D, dA. Now we have to go back to our methods for double integrals and figure out whether that region on the xy plane is y simple or x simple. Remember that if that region D is y simple, then over some interval for x, let's say from a to b, y always varies from one function of x, g1 of x, to another function, g2 of x. That will finally allow us to take this triple integral and iterate it fully into dz, then dy, then dx. We'll be careful with this order and our boundaries. Now, our first operator in order of operations is this integral closest to the function with respect to z, where z ranges from u1 to u2. Then we get rid of one variable and we'll end up with a result in x and y. The next operation will be integrating with respect to y from a function g1 of x to g2 of x. And when we evaluate that definite integral, we only have the variable x remaining, and finally we'll integrate from x equals a to x equals b, leaving us with a numerical result. We shouldn't have any variables left over in this evaluation. Now that is dz, dy, dx order, but there is another order that could happen from a z simple region. If we go back to this step here where we converted our triple integral into a double integral, then that region D could potentially be x simple. If D is x simple, then over some interval for y, let's say from C to D, x will range from one function h1 of y to another function h2 of y. And those will be our boundaries on x, and we'll integrate with respect to x right after we've finished integrating with respect to z. So once again, being very careful of our order of integration, we will integrate with respect to z first from u1 as a function of xy to u2 as a function of xy, eliminating z from our expression, and then we'll integrate with respect to x as a function of y, h1 of y to h2 of y. That will eliminate the variable x from our expression. Now we only have an expression involving y, and we finally integrate from y equals c to y equals d, and that definite integral will evaluate to just a numerical result now. So we see two orders already, dz, dy, dx, and dz, dx, dy, depending on whether or not the three-dimensional region E is z simple, and whether or not the two-dimensional region is y simple or x simple. Now, those are only two orders so far. Let's just quickly imagine what kind of orders we would get, whether this three-dimensional region E is y simple or x simple. Now, a y simple region in R3 is very similar to a z simple region in R3. Over some region D, this time on the xz plane, y will always range from a function u1 in terms of x and z to a function u2 in terms of x and z. Those are two surfaces given in the form of y equals a function of x and z. Now, that region D on the xz plane could either be z simple or x simple, and that will give us two different orders. We could potentially have dy dz dx or dy dx dz. We'll first have to decide that this region is y simple, and then look at the xz plane and see whether or not that two-dimensional region is z simple or x simple. Finally, this three-dimensional region E could potentially be x simple. If our region E is x simple, then over some region D on the yz plane, x will always range from a function u1 of yz to another function u2 of yz. These are, again, two surfaces, and these surfaces are given in the form of x equals a function of y and z. Once we take a look at those two boundaries, we'll have to view the region of integration on the yz plane and determine if that region is y simple or z simple. That finally gives us the last two orders, dx, dz, dy, and dx, dy, dz. Now, I do find that oftentimes the trickiest part of triple integrals is setting up the boundaries of this region of integration, determining whether or not that region is z simple, y simple, or x simple. Now, z simple happens fairly frequently because we often use surfaces of the form where z is a function of x and y, but that's not always going to be the case. So I've set up a little maple worksheet here to give you an idea of a couple regions and what they look like in three-dimensional space so that you can determine whether or not you should iterate with respect to z first, y first, or x first. Over here I've got region 1 and region 2, and I'm going to need to use the plots package. Let's take a look at this first region and determine whether or not we should be treating this region as z simple, y simple, or x simple. So we have this sort of first octant view. Z is already pointing upward. And let's see whether or not this region is Z simple. We're going to take a look at the top of the Z axis first, looking down on the surface to determine if there is a consistent top surface. And then we'll flip that upside down and we'll take a look at the bottom of the Z axis, looking up at the solid to determine whether or not there's a consistent bottom surface. So, taking a look at the top here, from a positive z-axis, you can see that this region always is bounded by this blue surface as its top surface. And then we'll take a look at the bottom, and looking from underneath here, we can see that this red surface is always the bottom surface. So it's definitely z simple, and if we're spinning this object around, you can see that no matter which way we look at it, the blue surface is always on top. Now, let's determine whether or not this region could potentially be y simple. I'm going to rotate this y-axis so that we have a positive y value at the top of the screen and a negative value of y at the bottom of the screen. We're going to take a look at this solid region from the highest value of y first, looking straight down. And you can see there's a little bit of this blue surface sneaking through. The top surface is not consistent. If we wanted to iterate with dy first, we'd actually have to split this triple integral up into two separate regions. One where red is the top surface and one where blue is the top surface. And you can see as we rotate around, here is that problem. There is a potential where this blue surface is the highest value and the lowest value of y in some region of E, this particular solid. So it's definitely not y simple, and that would be a poor choice of variable to integrate with first. Now let's take a look at whether or not this region is x simple. We'll reorient this so that the highest value of x is at the top of the screen. And let's look from top-down view at the highest value of x everywhere in the region. We can see the highest value of x everywhere in this solid is red. The lowest value of x, if we flip this upside down, is always along this green surface. So this region is actually both z simple and x simple. We can see that there's a consistent boundary surface for x from highest value of x to lowest value of x. And we can see that there is a consistent boundary for the highest value of z and lowest value of z. Okay, well let's take a look at region 2 now and see whether or not we can determine z simple, y simple, or x simple. There's a lot more curved surfaces going on in this one. Again, we've got this first octant view where z is already oriented towards the top of the page. So let's take a look at top-down view. Looking straight down from the highest value of z, we actually see a potential of 4 different top surfaces. Right away, this would tell us that this triple integral would have to get split up into 4 separate regions if we wanted to iterate with respect to z first. That sounds like a terrible thing. So we're not going to treat this as Z simple. Let's reorient this so that the y-axis is pointing straight up. Now, looking at this solid region from the highest value of y, we have one surface, which is the blue surface. Looking at this from the lowest value of y, again, we just have one surface, the red surface. So this region is y simple. If we rotate that around, we can see that the blue surface is always at the top and the red surface is always at the bottom. Now, is this region x simple? Rotate this around so x is now pointing at the top of the screen, and look at this from top-down view. Here's the highest value of x at every point in the solid. Sometimes the highest value of x is on the purple surface, and sometimes the highest value of x is on the red surface. So this particular region is definitely not x simple. You can see that from spinning this around that sometimes purple is on top and sometimes red is on top. So this particular region would only be very good to integrate with respect to y first. Now I have another tab open here to show you a region that is z simple, x simple, and y simple. This is the best case scenario. We can see we have a top surface for z, which is blue, and a bottom surface, which is red. If we're taking a look along the y-axis, the right-hand side here is positive y. This surface is the highest value of y, which is blue, and we have a purple surface, which is always the lowest value of y. And finally, rotating this around so we can see x, our lowest value of x at x equals 0 is always this green surface, and the highest value of x, well, is actually also the purple surface again. This region, no matter how we rotate it around from any orientation with z, or with y, or with x, we can see that there's always a consistent higher surface and lower surface in that particular direction. Now, because this particular region is x simple, y simple, and z simple, it provides a pretty good region for us to try a practical example of triple integrals. Now, I'm not going to focus on the technique of integration so much, but let's see if we know how to set up a triple integral over this particular region. So here, I don't actually have a function f of x, y, z in mind, but let's see if we can take this triple integral and set up iterated integrals in all 6 different orders, where E is the region bounded by the cylinder y equals x squared. That's a parabolic cylinder. And the planes z equals 4 minus y and z equals 0. Z equals 0 is just the xy plane. For x greater than or equal to 0. This will actually just put us into the first octant. And it's precisely that region that I just showed you in Maple. But let's see if we can try to sketch it ourselves. A good way to try to sketch a cylinder like that is to maybe just draw a sketch of that particular curve on the xy plane. Y equals x squared would be a parabola opening upward towards the positive y-axis. Now we can imagine that that's a cylinder that extends infinitely into the positive and negative z direction, but maybe let's try looking at what this plane will look like as well to get a sense of where the two surfaces intersect. Now, z equals 4 minus y is nothing more than just a line on the yz plane. That's pretty easy to graph from this particular sketch. That would just be intersecting the z-axis at 4 and sloping downward in the positive y direction with a slope of minus 1. If you want to try to put that into a sort of three-dimensional perspective, then here's a portion of that plane sloping downward towards the positive y. Finally, we can kind of get a sense of where the two surfaces so far intersect. This parabolic surface will intersect this blue plane in the shape of another parabola, something like this. And we only need to consider for x greater than or equal to 0 and bounded by z equals 0. That just gives us half of this particular cylinder that I've drawn. We can try to graph that boundary of x equals 0, and that will be this sort of triangular region. And now we should have a pretty good idea of what this shape looks like. I'll just try to trim off some of this excess area here. Finally, I'll add a little shading to this top surface. Okay, it's not quite as good as using Maple, but it gives you a pretty good idea of what this solid looks like. Now, let's start off with maybe our favorite example of what to integrate with first. Let's treat this region as z simple. If we're going to treat this region as z simple, we first need to figure out what the top and bottom surfaces are. And we can imagine looking downwards from the positive z here and seeing this particular plane. That's the plane z equals 4 minus y, and that's already a surface in the form of z equals a function of x and y. Since that's our top surface, z will be less than or equal to 4 minus y. Now, looking from below, we should see that the xy plane is the bottom surface. And that is just z equals 0. That's already, again, in the form of z equals a function of x and y. So z is always going to be greater than or equal to 0 for every single point in this solid region E. Now, what is the two-dimensional region of integration that we are left with? Well, whether or not we are looking at this from above or below the xy plane, we should see that the region of integration on the xy plane has two flat sides and one parabolic side. Here's what that particular region D would look like. Over every point in this region, though, we know that z is bounded by 0 and 4 minus y, those two surfaces. Looking at this region D, we could try to treat this as y simple with vertical cross sections or x simple as horizontal cross sections. We're going to have to consider both. But let's see if we can come up with the equations of these three curves. The purple curve might be easiest. We already visualized that parabolic cylinder as simply just a parabola on the xy plane. That's all this is. It's just the intersection of that parabola, y equal x squared, and the xy plane, which is z equals 0. So the equation of that particular curve is y equals x squared. Now, what about this green line? That green line there corresponds to the intersection of the yz plane and the xy plane. So that's really just the intersection of x equals 0 and z equals 0. On the xy plane, well, that's just x equals 0. And you may not actually have to word that as the intersection of two surfaces if you already realize that x equals 0 is the boundary here. Finally, this blue line. That one might be a little bit trickier. That blue line, looking at this three-dimensional picture, is where this diagonal plane intersects the xy plane. So that's the intersection of this function z equals 4 minus y and z equals 0. If we set z equal to 0 in the equation z equals 4 minus y and solve for y, that gives us y equals 4. And sure enough, that's the equation of that line now. Now, at this point in time, we have the equations of all three different boundaries of that region D. It may also be good to know where each of those boundaries intersects each other, and those are going to be points. Clearly, we can see when x equals 0 and y equals x squared intersect, we must have y equals 0. So here's our point 0, 0. When y equals x squared intersects y equals 4, then we would have to have 4 equals x squared. X in this case has to equal 2 since we're looking for positive x. So this gives us another point here, 2, 4. And finally, when x equals 0 and y equals 4, well, that's the equation of our third point here, 0, 4. Now we're ready to try setting this up as potentially being y simple. Treating this region as y simple, we see that over an interval for x from x equals 0 up to looks like x equals 2 here, y will always range from a bottom function, x squared, to a top function, 4. That gives us our boundaries on x and y. So, treating E as z simple and D as y simple, we have the boundaries for z from 0 to 4 minus y from x squared to 4, and x from 0 to 2. If we wanted to treat D as x simple, though, then for an interval for y from 0 to 4, our boundaries on x will go from x equals 0 up to this purple curve, where x is equal to the square root of y. See, we always have to try to solve for a function. X equals a function of y in this case. That changes our boundaries of integration. For an interval from y equals 0 to y equals 4, x will range from a function x equals 0 to a function x equals root y. And here is the resulting triple integral in iterated form. All right, well, 2 orders down, let's see if we can take a look at this region as a y-simple region now. Taking a look at this three-dimensional sketch again, let's see what the boundary surfaces are for y. Now that's kind of oriented to the right and left-hand sides of the page here. The farthest right-hand side, well, at any point in time in this particular solid region, the rightmost surface would be this blue surface. That was the equation z equals 4 minus y. But we can take that and express that in the form of y equals a function of z. Y equals 4 minus z. That gives us our upper boundary on y now. Now, as for the lower boundary on y, if we were to take a look at this whole solid region from the far left, looking at this kind of from the negative y-axis looking at the region, we should see this purple surface is always going to be the bottom boundary for y. Now that is the cylinder y equals x squared. That is already in the form of y equals a function of x and z. So that is our bottom boundary surface. Y ranges from x squared as one surface to 4 minus z as another surface over some region on the xz plane. And we can call that region D. Now, let's see if we can try to sketch what that region looks like on the xz plane. That's going to be a little bit tricky here because x is oriented sort of towards us out of the page and z is oriented towards the top of the page. Now here's my sketch of that region D. And it might not be super accurate, but we can kind of see that if we're looking at this region D, maybe from the negative y-axis, we can see having x oriented to the right of the page and z oriented to the top, we end up with two flat surfaces. One of them should be just along the xy plane. One of the flat surfaces should be along the yz plane, and then we should have some kind of a curved surface, which may be a little bit hard to visualize at first. But that curve is going to be coming from the intersection of the purple cylinder and the blue diagonal plane. Why don't we start off with that surface first? If we're not too sure what that curve actually is, remember that that purple curve is the intersection of y equals x squared and y equals 4 minus z. Well, that allows us to set those two equations equal to each other and give x squared must equal 4 minus z. If we want to treat this region maybe as z simple, we could easily represent that as z as a function of x, 4 minus x squared. If we want to treat this as x simple, that might be a little bit trickier. Now, what about these other two particular lines? Since they're just straight lines, they're pretty easy to understand because they are simply just the yz plane and xz plane, but we can also tend to think about those as intersections if we like as well. This green line here, we could imagine that as being the intersection of this green surface and this purple surface, the intersection of x equals 0 and y equals x squared. That just gives us the equation of that line as x equals 0. This blue line here is really just when z equals 0. But if we wanted to, we could always determine that line as really like the intersection of the surface 4 minus y and the surface at the bottom, z equals 0. For more difficult regions, we are often trying to determine these equations using intersections, but in this case, since several of the sides are simply just flat, it's a little easier. Z equals 0 and x equals 0. The last thing to do before we iterate is maybe just to find the intersection of these three curves on the xz plane. When x equals 0 and z equals 0, well, we'll have the origin, obviously, 0, 0. When we have z equals 0, but intersecting z equals 4 minus x squared, that gives us 4 minus x squared equals 0, and x has to equal 2. So this will get you the point x equals 2, z equals 0. And finally, we have the intersection of x equals 0 and z equals 4 minus x squared. So that would be the coordinates x equals 0, z equals 4. Now we're ready to try setting this up maybe as z simple, since this particular purple curve was best represented in the form z as a function of x. Our interval for x ranges from 0 to 2, and our boundaries for z go from this blue function, z equals 0, up to this purple function, z equals 4 minus x squared. And that gives us our boundaries on z and x, with our initial boundary here for y from x squared to 4 minus z. That gives us the order dy, dz, dx. Now, it may not be quite as optimal to set d up as an x simple region. That would simply be because z equals 4 minus x squared is probably a lot nicer than solving that same equation for x to get a function x equals f of z. But if we wanted to solve for x, then we could always say that x is equal to the positive root of 4 minus z, since we know that x must be greater than or equal to 0. Then, for an interval from z equals 0 to z equals 4, x will range from x equals 0, the green function, to x equals root 4 minus z, the purple function. That gives us our iteration order dy, dx, dz. The interval for y hasn't changed since we treated e as y simple, but we have x from 0 to root 4 minus z, two functions, and z from 0 to 4, two constants. With 4 orders down now, there's really only 2 left, but we have to go back to the solid region E and treat it as x simple now. To get our last 2 orders of iterated integrals, we want to try to determine what the 2 surfaces are that bound this solid region for x. Now we're already looking at this region from the positive x-axis, and we can see that the surface that's closest to us from the positive x-axis is this purple surface. That purple surface has the equation y equals x squared. That's not already in the form of x as a function of y and z though, so we'll have to rearrange and get x equals root y. Since we know x is greater than or equal to 0, we don't need the negative root. Now, the surface that's farthest away from us, or if we wanted to put our vision in the page looking out, we should be seeing this green triangle. That green region there is the surface x equals 0. That gives us our boundaries on x. X ranges from one surface, x equals 0, to another surface, x equals root y, over some region D on the yz plane. And it's actually pretty easy to see the yz plane since it's actually pretty much in its proper orientation already in this particular view. And here is that same region. You can see that we basically have a nice triangle here. There's 3 straight sides. It's actually a pretty nice region to try to integrate over now. The diagonal line here is really just that particular plane, z equals 4 minus y, but intersecting the yz plane when x equals 0. Now, of course, we're really just looking at a region already on the yz plane, so the equation of that line simply is z equals 4 minus y. That's already set up so that z is a function of y, and it's pretty easy if we want to set that up so that y is a function of z. Doesn't really matter whether or not we want to treat this region as y simple or z simple. We have 2 other straight sides, and we don't necessarily have to think about them as intersections, but generally speaking, it's not a bad idea when the surfaces aren't just simply flat coordinate planes like this. This green line here is the xz plane, but we can also imagine that as simply just being the intersection of the purple parabolic cylinder and the green plane. That's the intersection of y equals x squared and y equals 0. That line here on the yz plane is simply just the line y equals 0 though. This purple line here at the bottom, well, that is just the xy plane. It's simply when z equals 0. Z equals 0 is both a surface and a line depending on whether or not we're talking about 3 dimensions or 2 dimensions. So right away you can say for sure that this line is simply just z equals 0. But generally speaking, if you want to think about that particular line as the intersection of 2 planes, that would be the intersection of the blue plane here and the green plane, the intersection of z equals 0 and x equals 0, which on the yz plane is just the line z equals 0. To complete all the boundaries, let's take a look at the 3 points that form the vertices of this triangle. We have the origin. When z equals 0 and z equals 4 minus y intersect, we must have to have y equals 4. And when y equals 0 intersects z equals 4 minus y, we must have z equals 4. Now, because we have z set up as a function of y, let's try treating d as z simple first. over an interval for y from 0 to 4, z will be bounded by the purple function and the blue function. Z will have a minimum value along the function z equals 0 and a maximum value along the function z equals 4 minus y, where y varies from 0 to 4. That will give us the order dx, dz, dy. Finally, if we wish to express that z equals 4 minus y in the form of y equals 4 minus z, then we can see that y is now a function of z, and we can treat the region as y simple. When z ranges from 0 to 4, y will range from this function y equals 0 in green to this function y equals 4 minus z in blue. That gives us our final order, dx, dy, dz. You can see y ranges from 0 to 4 minus z, and z ranges from one constant 0 to another constant 4. In all 6 of these different orders of integration, we should make sure that we end up with a constant. We are always dropping a variable as we integrate each individual integral until we should end up with a constant. Now, this is a very difficult process, and obviously it's a very lengthy process, as you can tell from the length of this video. Worthwhile to just try lots of examples and see which of the iterations makes the most sense. It's not necessary to actually figure out all 6 iterated integrals unless you're specifically asked to do so. You should try to determine whether or not there are easy boundary surfaces in z, y, or x first. Get that out of the way. And once you've taken a look at the boundary surfaces, you can visualize the region of integration on a 2-dimensional plane. xy, yz, or zx. One of those particular planes will then allow you to determine if the resulting 2-dimensional region is x simple, y simple, or z simple. So, like I say, it's a complicated process, and of course there are regions in 3 dimensions that may not be very simple in x, y, or z. There are other coordinate systems out there that will allow us to evaluate triple integrals more easily when something has kind of a rotational symmetry, much like polar coordinates for 2 dimensions. But we'll hold on to that for a future video, so stay tuned. Thanks for watching, and I'll see you in the next video.